So I'm going to get started here in a minute, but just to let everybody who's sitting in the back know, what's in the red book's a little bit different than what I've got now. I've tweaked it. I've added some ethereal screenshots. So if you're interested in reading, you probably want to be about at least 3/4 of the way towards the front. We'll get started. So sorry to be planted in one spot, but the mic's dead on the wireless mic, so hopefully they'll fix that at some point. But till then, I'll be firmly planted behind the podium. So to start out, who here thinks VLANs are insecure? Come on, more hands. Okay. So that was the assumption that we went in before we started doing this talk, was that we had insecure VLANs, basically. We had folks who were looking at layer 2 security and were basically saying to themselves, all right, I've got security built into my network, and now I want to try and do things at layer 2, and I want to rely on VLANs for separation. And so what can we do about that? So what we went through and tried to figure out, also if you can try and take a look at that screen, it keeps flipping on and off every few seconds. Anyway, so what we did was we basically said, all right, well, Cisco can go through, and by the way, my name is Sean Convery, and I'm a security researcher in Cisco in our critical infrastructure assurance group. So we basically work with national labs, universities, private industry to try and figure out how to make the infrastructure a little bit more secure. So what we decided to do is, well, Cisco can do testing ourselves, but that is a bit problematic because if I stand up here and say, well, VLANs are secure, and we tested everything out, then raise your hand if you would believe me. No hands, right? So we decided to. Let me see if this works. Hello. All right, great. Sorry about that. All right, can everybody hear me now? Okay. So what we decided to do was try and figure out, who can we go to try and get us to help. So At Stakes presented a couple of times. They've got a good reputation. So we basically handed them a big bag of money and said, break VLANs, please. Try and figure out some way to get traffic from one VLAN to another VLAN. We had them do some of that testing. Cisco internally, we did a lot of the other testing we're going to talk about. What we're basically going to present over the next hour and a half is the results of the testing that we did, focusing on how to stop the attacks. One of my big pet peeves with conferences like this, and I've been to a few, is everybody stands up here and says everything's screwed, and they don't tell you what to do. So how many people here are actually responsible for the security of a network somewhere? Okay, keep your hands up, by the way, if that's your only job, if you don't do anything with a network. Okay. How many actually, I'm big on polls, sorry about this, I'm going to get an arm workout. How many folks work in an organization where they have a separate security department from the networking department? Keep your hands up if they get along. Okay, like 6 or so. So we'll talk a little bit about that because as you can see, I'm going to talk about a lot of security features that you can put into Ethernet switches that are sort of places that the standard SecOps guy wouldn't necessarily think is his domain. The networking guy definitely thinks is sort of his bailiwick, but he's not going to be that interested in dealing with the security features. So we're going to walk through kind of in general why we should care about layer 2 security. We're going to actually go through every layer 2 attack that we're aware of and talk through some of the mitigation techniques. You'll find that some of the ways we stop the attacks are kind of messy. Some of them are fairly clean. And we'll talk a little bit about some of the roadmap stuff that we're working on. All right, so some caveats here. This is assuming IP and assuming Ethernet and assuming a switched environment. So if you're running AppleTalk or IPX, I mean, great. You probably have different things you're vulnerable to. Some of the same things we're talking about are probably going to affect you as well. So we did all the testing for obvious reasons on Cisco devices. We found that vendor resiliency to some of these attacks we're going to talk about is going to vary widely. So it's going to depend a lot on the box you're buying. If you're going to CompUSA and buying a $100 Ethernet switch, you're not going to be able to expect to do a lot of the features that we're talking about. So I thought about going through and listing all of our competitors and whether or not they support given features or don't support given features. But in the end, I decided not to do that. If you're interested in, does vendor X support this feature, just come and talk to me afterwards, and I'll give you the best of my knowledge. The trouble is, if I tell you somebody doesn't do something, invariably, like last week they released it, and then I look like an ass standing up here telling you that, X vendor doesn't support some feature. All right, so why do we care? Layer 2 security is interesting because, you know, I sort of shudder to put an OSI model in front of the black hat crowd. But basically the point is that the OSI model was built for all the different layers to operate without knowledge of one another, right? We wanted to make sure that the physical layer, the data link layer, the network layer, all these guys kind of happily coexisted, but didn't need to know a lot about each other. The trick is if we hack one of these layers, we tend to get the rest of them for free. There's an obvious exception here. Somebody? Well, all right, physical. So there's an obvious exception. I'm thinking to layer 2. So let's assume I hack layer 2. Generally, in most cases, I'm going to get all the rest of the layers for free, except in one case. Encryption, right? If I do encryption right and figure out a way to distribute the keys before the session gets built, we'll find that you have some improvements in the way you can deal with attacks. We're going to see as we go through some of this that some of the attacks we talk about actually break some of the encryption. So we'll see in cases where that works and where that doesn't. So like I said, you get layer 2, you get the rest for free. So where this gets even more interesting from a problem standpoint is when you're trying to deal with network ops and security ops, right? So that's why I asked that question at the beginning. If you're a network operations guy, you basically are thinking to yourself, well, I deal with the network, and the security guys deal with security. They have their own boxes that they deal with. They're very protective of their boxes. I'm very protective of my boxes. And I basically try and figure this whole thing out using my own networking gear. And if the security guys come to me and ask me for addresses, I just give them a port, I burn the subnet for them, I give them a VLAN, and send them on their way. And most of the security guys, aren't dealing with layer 2 attacks. They're staying at layer 3 where their comfort level is. And when they look at what's going on at layer 2, they don't even deal with the network operations guys. They just say, hey, I need an IP address, and they don't really care where they get it from. So they're given an address, they're given some ports and some ranges, and from that they try and build their security. So what we're seeing, and most of the time I'm running around talking with large customers around the world about security design and security architecture, and I find that these security operations guys and the network operations guys just don't get along. In some cases they're hostile. And this can be very problematic, particularly at layer 2, because the solution to layer 2 security is not to put a firewall everywhere or to put intrusion detection everywhere, because it would just be cost prohibitive. So we have to talk about some of the other ways we can deal with security. I don't know if anybody else can get somebody in AV. This has got to be killing you guys to have this thing blinking on and off, so help. So CSI FBI, so this is a study. Some people put more stake in this than others, but has anybody here heard from a security vendor 80% of all attacks come from the inside? Okay, bullshit, right? So, I heard this, and I've been hearing this for years from people inside Cisco, from people outside Cisco. And then I went and tried and figured out, where did this all come from? And I can't find any statistics to back this up. So if you have something afterwards, I'd love to hear about it. What we do have is this CSI report, and they ask this question every year since they started doing this in '96. And what they say is, by what location would you consider a frequent source of attacks? You can see there, internet's on the rise, dial-ins going down, and internal systems are going down. Still 33% of all respondents say the internal network is a frequent source of attack. I would theorize, though I don't have any data to back it up, that the impact of an internal network breach is far more damaging than the impact of an external breach. So it's an interesting research project if someone has some free time. So let's talk through some MAC layer attacks. That's going to be the first category of attacks we're going to walk through. Sorry, that Big Mac looks tasty. I haven't eaten yet. I can never eat before I present. So quick review, MAC addresses I'm not even going to talk about. Hopefully everybody here understands that. The CAN table. How many people here know about CAN tables? Content addressable memory. What this is the mechanism within switches where they sort of control basically the addressing information for what MAC addresses and what VLANs are connected to which ports. Think of it like a routing table for a router. So you basically have this table that walks through and says, here's the MAC address, here's the VLAN, and this is the port that they're connected to. So the trick is these things have a fixed size. So in normal behavior, let's assume that we've just got a CAN table that will only hold 3 entries, which would be particularly useless. But let's say 2 out of the 3 are taken up right now. So I've got MAC A in port 1 and MAC C in port 3. So let's say A tries to talk to B. What's going to happen is the switch doesn't know where B is, so it's going to have to flood the frame. So it floods the frame out to B and C, And then C gets to see the traffic, right? This is the core thing. This always happens for the initial packet when you don't know the destination MAC location. So this is normal behavior. What's going to happen, though, is MAC B is going to respond on port 2, and the switch is going to learn the location of MAC B. So he learns that location, adds it in to his CAN table, and then sends the traffic on to MAC A. So from this point on, A tries to talk to B. The entry's already in the CAN table, giving the location, and now MAC C won't see the traffic to MAC B. That's the basics of a CAN table and how the CAN tables are built in a dynamic way to understand the locations of different addresses. So the CAM overflow attack is the idea that says, well, let me just send it so many CAM entries that it can't deal with them all and starts having to flood traffic. Everybody here should hopefully be a little bit familiar at least with the basics of how this works. So this is the theoretical attack, but as most attacks turn into the practical very quickly and usually with very few lines of code. Somebody went through and built MAC off using Perl back in '99. And what it basically does is it just generates bogus packets with a bogus source MAC, bogus destination MAC, bogus source IP, bogus destination IP, sends it out on the wire. Doug Song later converted this, ported it to C for DSNF, which we'll talk about later. So here's the idea. Let's assume that the MAC table is completely filled right now. A, B, and C each have an entry. Now, one thing to understand with the way MAC tables work is they have aging timers. So MAC addresses are going to age out over time. The default is 300 seconds. So if you don't talk on the wire after your address is learned by the switch, after 300 seconds, it's as though you were never there. The next packet that comes in with the destination MAC of your MAC address will get flooded until they relearn your location. So this is going to, let's just assume for this attack that everybody's aging timer is about to age out, which will make this convenient because this is just trying to show you the basics of how it works. In normal cases, if people are chatty, they're never going to lose their CAM entry because they'll keep refreshing that aging timer. So MAC C spoofs a packet from source MAC X, sends it off to the switch. The switch learns X is on port 3, updates his CAN table. Happens again from port Y. Y is a spoofed MAC source from MAC address C, gets sent on the wire. Again, the switch learns that Y is on port 3. And now at that point, the MAC table is completely filled with all entries on port 3. So when the packet gets sent now from A to B, we have the same condition that we had in the initial flood state, where that packet gets sent out on all ports till we learn the location of MAC address B. So the way Catalyst CAN tables work is a little bit interesting. It's useful to understand this. Basically, they have this notion of 8 buckets or 8 columns and 16,000 rows to hold CAN table information. And what they store in those CAN tables is the VLAN and the MAC address of the given MAC address or the given address, and they also hold the port number, right? But in order to make this fast, what happens is they hash the values, right? So they take the MAC address and the VLAN and hash it. They take basically 63 bits of source, and then they turn it into a 17-bit hash value that they then use to index the list so they can search through the list quickly. So anytime you're taking 63 bits of source and turning it into 17 bits, you're going to have collisions, right? You're always going to have cases where that 17 bits is going to be the same. So when that 17 bits turns out to be the same, what happens is it gets sent to the next column, right? So you hash that value, that 17-bit value determines what row you go into of the 16,000 rows. And then based on if it's a duplication, you wind up putting the packet into the next column over. So in theory, you could actually cause a switch to flood with as little as 9 MAC addresses, right? If you had the right combination of source material that always hashes to the same value, and you did that 8 times in a row, when that 9th packet comes down and tries to find a place to go into that CAN table, it won't find one and it'll wind up flooding. So that's the basics of how the hash function works in the CAN tables. And this example is for a CAT 6500. Different switches have different MAC address or CAN table spaces. So some of the lower end switches are like 8,000 MACs instead of a higher number of MACs. Could I ask you in the front, can you see if you can do something about that screen? It keeps flipping on and off, and these guys are probably on the verge of insanity. Thanks. So this is a tool far too difficult for a script kiddie to run. You actually need to type MAC off and hit enter, and then the attack is launched. So very, very difficult. And as you can see there, it's almost like TCP dump output. The SYN flag is set, so you get sort of a SYN flood for free as part of this attack. So DSNF in the testing that I did could generate 155,000 MAC entries per minute. And we already talked, we had 16,000 rows and 8 columns, so roughly 128,000 entries. It turns out it's 131,052, I think. And if this was a perfect hash function and the data was perfectly random, this would fill up in a nice even ordered session. We'd go through 16,000 rows and we'd go to the next column. In actuality, because the data is a bit clumpy and the hash function isn't perfect, we wind up taking about 70 seconds to fill. So we'll basically flood on certain rows much more quickly, and it'll take time before everything will get populated. But basically, after 70 seconds, the CAM table is completely filled. So what this means is any traffic that doesn't have an existing CAM entry will flood all the packets, right? The important thing to note is a lot of times when people talk about this attack, they don't give you the details. They will flood, but only on the local VLAN. So if we're broken out VLAN 1, 2, 3, 4, and somebody in the back row completely destroys the CAM table that we're all connected to, each of us is going to see all the traffic within our VLANs, but we won't see traffic from other VLANs. So that's an important thing to note. It's one CAM table for the whole switch, but the flooding is always local. Because there's no reason for the switch to flood on all ports, because all it needs to do is flood it out to its local VLAN to try and learn the location. So the idea is if I just keep running this MAC flooding over and over and over again and just leave it running in the background, there'll never be any room for new CAM entries. So all new PCs, all new systems will basically flood. Typically, something like a default gateway, for example, will probably not flood because he's going to be talking all the time. Really chatty servers may not flood. But basically, everything else is going to flood. And over time, more things will flood as people stop talking. So if I was on the network today and I went home for the day, I'll age out my entry in 300 seconds. That'll be another one that the CAM table flooding software will be able to grab. I come in the next morning and now I'm flooding as well. This is a very, very noisy attack, by the way. I mean, you've got traffic everywhere. If you have multiple switches, all the switches get flooded. You get all kinds of strange messages on the consoles of your switch talking about no room for things. So it's definitely not something, if you're trying to be particularly stealthy, that you would want to run. So here you can see the snoop output down at the bottom on a non-span port. And you see a ping between 26 and 25, and this guy's .50. So this is just some testing that we did. All right, so stopping this attack is actually not all that difficult. How many people here are actually using port security? All right, not too many. So port security, many people get scared because when they think of port security, I include myself in that group up until about a year ago, I thought that port security meant that I had to build MAC address tables, right? I had to build a table of every single MAC address that was connected to my network and then assign basically VLANs or ports based on those source MAC addresses. While you can do that, you'd have to be insane. Because as anybody knows, once you get beyond a couple hundred people, or 10, depending on your tolerance for pain, you're not going to want to deal with this, right? Because somebody's NIC goes bad, you've got to swap them out. It's just really messy. But what you can do is instead say, here is the maximum number of MAC addresses that I'm going to allow to connect on a given port. And that's a lot more reasonable, because now I can just say, all right, this guy is supposed to be connected to a user port. He shouldn't be plugging in switches. He shouldn't be plugging in other devices. Maybe I'll be nice and give him 2, 3 MAC addresses, but certainly won't give him 131,000 entries. So if you want like a couple hundred pages on port security, that link at the bottom will fulfill that need. The configuration is fairly simple. You can see the configs for CatOS and then also for native iOS on the switches. Depending on the platform, you'll have different capabilities. But basically, you see here, you just say set port security, then the ports, and you turn it on or off. You can set a MAC address, but like I said, please don't, because you're gonna kill yourself. You can set the age, how long it will allow that MAC address to be resident before it ages out. The maximum number of MACs here, this is the one you actually want to play with. And then you have to set whether or not you want to shut down the port when it goes into violation, or if you just want to restrict. I would recommend dealing with shutdown. If somebody's MAC flooding your network, don't be nice and try and let his first MAC address through. Just shut it off. The reason I suggest that, besides just being common sense, is I was able to peg a Cat 4000 at 70% CPU utilization with MAC off in restrict mode. Because the switch and software is constantly trying to look through, is this a good MAC? No, throw it on the floor. Is this a good MAC? No, throw it on the floor. It keeps doing that over and over and over again. So better to just turn the port off. You can set the port shutdown timer to whatever you want. You can set it to fire off an SNMP trap. Works pretty well. Well, I also found that depending on the version of code, the restrict option eventually gave up anyway. So if you just MAC flooded over and over and over again, it would just eventually say, look, I can't even keep track of the good MAC address, so I'm just going to shut down this port. And there's no performance impact to doing it in shutdown mode because it's just like you administratively shut it down yourself as the administrator. It just turns the port off and it doesn't do anything. And then I went through, for all these slides, I'm not going to talk about it, but I went through and did all the hard work for you in walking through the Cisco docs. So if there's a particular flavor of switch you're trying to know, is this feature supported on my switch? That's the minimum releases of code you need to support the different features. All right, so VLAN hopping. We're going to go through some of the attacks that people know about and one that I don't think too many people have seen. So quick trunk port refresher. Trunk ports basically allow multiple VLANs to span over a single physical link. That's the basics, right? I've got 2 switches. I've got 3 different groups at each switch, and I need to allow them to talk to one another. Rather than using 3 cables, I can run it all over 1 cable, set it as a trunk port, and I'm done. You can use 802.1q, which is the standards-based way. You know, some people are still using ISL, which was Cisco's proprietary version. You also need to know about Cisco switching control protocols. This is one of the new slides. So these are typically IEEE 802.3 packets with 802.2 LLC and SNAP that are basically used to exchange all kinds of information between switches. CDP uses this, VTP uses this. We're basically using, our DTP uses it as well. These are being used to exchange information basically at the link layer between the switches so that they can know what VLANs are available, what trunking parameters are available. So as we go through this talk, you'll see the SNAP protocol type and the destination MAC address for each of these protocols. And you can see them real easily. Most of them are decoded by Ethereal. The other thing to point out with these control protocols, and this gets to one of our best practices, is I always recommend folks don't use VLAN 1. VLAN 1 is a little bit peculiar on Cisco switches at least, and that first off, it can't be deleted. So I never want to put users on a VLAN that if things go bad, I can't turn it off. Right? So that's the first thing you need to be aware of. The other thing is that even if you turn it off, some of these control protocols will keep using VLAN 1 and just not tell you because they're coded to use VLAN 1 and that's all they'll ever use. So if you're trying to deal with segmenting your user traffic off from your control traffic, just in general, I would recommend your trunk ports and your user ports do not use VLAN 1. Unfortunately, you know, people aren't doing that today, and we haven't exactly done the best job of making that very easy to configure. One of the concerns that I have, and one of the things we're trying to change at Cisco, is that routers and switches try and make things happen, right? They want to switch, they want to route, they want to talk to people. Firewalls and IDS systems are trying to, you know, restrict traffic or be more like security devices. So one of the things we need to do as a networking company, particularly as the network gets relied on more and more to do security functions, is to make it easier to make it secure. We need to make it easier to have either secure defaults or an easy macro that you can just type something in and hit enter and have all these best practices implemented for you. Because right now, although folks in this room would have no problem locking down a switch or a router, you know, the average guy out there at a small law firm that's hooking up a switch and a router is going to have all these things configured in the wrong way. And then all the attacks I talk about are going to work fine. So for that reason, don't use VLAN 1. If you want more detail, again, link at the bottom, plenty of pages. And for the detail-oriented, if you want to see actually what this packet looks like, you can see how it's basically broken out. The destination MAC is usually a variant of that MAC address that you see there. The source MAC is actually pulled from a pool that's in the EEPROM of a Cisco device. And it's always set, you know, AA03, which is SNAP in terms of the LLC. And then you'll find the protocol type is really the only thing that varies in the SNAP header. The OUI is always the same. And again, lots of detail at that link below. So one of the first control protocols we need to talk about is DTP, Dynamic Trunk Protocol. This is the protocol that runs on most Cisco switches that basically controls who's allowed to trunk. By default, they're almost all set to auto, right? This is the bad thing, right? They're set to auto, meaning if you can fool the switch into thinking that you're a switch, it will allow you to trunk, and then you will become a member of all VLANs. It doesn't mean you automatically start seeing everybody's traffic, but you can now send packets on whatever VLAN you want. So that's one of the big issues with DTP. I haven't seen anything in the wild that would allow you to spoof DTP, but you know, you could plug in a rogue switch very easily, and these protocols are not particularly hard, so I'd be really surprised if somebody hasn't done it for some kind of an engagement. As you can see, the SNAP protocol type 2004. They can be set in other ways too. They can be set to desirable, which means they'll try and trunk if the other guy is willing to trunk. You can set them to off, which is what I would prefer folks set them to, or non-negotiate, which is basically used if you don't want to send out DTP frames, but you want to force it into a trunking mode. It doesn't work on the lower end 2900 or 3500 XLs. So the basic attack, this is the very easy one, which is through misconfiguration that it's enabled, is I can be at, say this is the attacker PC over here. All I basically have to do is spoof DTP, or if I'm using a switch that doesn't support DTP, the port has to be in a trunking favorable setting. If it's in some sort of a setting like on, you basically can then just tag your packets, .1Q packets, and send them on the wire. .1Q, if you're unfamiliar, just a little 4-byte tag that sits after the source and destination MAC address. You put the VLAN ID in, it gets sent on the wire, and the switch will think you're another switch. It will switch you to whatever VLAN you want. So this is the basic attack, and this will work on most switches that haven't been locked down and configured in a secure way, because for most releases of code, the default is to auto-trunk. There was a paper written by the SANS that the link's at the bottom if you're interested, that talks about another method of doing VLAN hopping. This method didn't work like a week after the paper was released, and this paper's 2 years old. So if anybody here is from the SANS, I'd love to talk to you afterwards to figure out how we can get this paper up to date, because we keep getting calls at Cisco, and I'm sure other switch vendors get calls as well saying, what about this paper, what about this paper? So there's a different attack that's a little bit more interesting to talk about, and this is a double encapsulated .1Q attack. Right, so this attack says, well, normally what's going to happen on a switch is a packet will be tagged if I'm a trunk port, and it'll be sent to the switch. The switch will look at that tag and say, all right, you say you're on VLAN 1, okay, and it'll send it on the wire. You say you're on VLAN 2, okay, and send it on the wire. But even if I'm not trunking, I can still tag packets as long as I tag them on my local VLAN. Anybody know why? There's another function that sits inside the .1Q tag. Priority, right? 802.1p also uses that 4-byte tag to set the priority from 0 to 7. So if I'm going to allow that to happen on my network, I have to always allow folks to tag traffic on their own native VLAN. So the way this attack works, and by the way, this works even if trunk ports are set off, is I send the tagged packet twice. So I've got this blue VLAN on the attacker, and the victim's over here on the orange VLAN. So my outer VLAN tag will be set to my actual VLAN, so my attacker VLAN, in this case VLAN blue. The inner tag will be set to the orange VLAN, which is the victim VLAN. So that gets sent. The switch looks far enough into the packet to see that first tag and says, oh, you're on the VLAN you're supposed to be on. It strips off the tag, sees that it doesn't know how to get to the destination MAC address, floods it out on all ports, including this trunk port. The trunk port sends the packet out on the wire, this time tagged with the VLAN of the victim. Now, this is the misconfiguration here in red. This only works if the trunk has the same VLAN as the attacker. This is another reason why we don't recommend you use the same VLANs for user ports as you use for trunk ports. So as long as you set, blue VLAN for the attacker and mauve VLAN for the trunk port, you'll be okay. So then the frame gets stripped off again, because now when the packet gets sent to the second switch, all he sees is the tag for the victim VLAN, and he has no idea that the original switch meant it to go on the blue VLAN, and then he sends it on the wire. We're bringing this up and talking about it as opposed to fixing it and not mentioning it to you guys, because this isn't something we're likely to fix anytime soon. This is a limitation in the hardware and the ASICs that actually control the .1Q trunking. So future generations of switching code hopefully will be able to fix this, but this is clearly a misconfiguration, and there's an easy way using Cisco or using general Ethernet switch best practices to get around this problem. So if you want to see what the capture looks like, you can see what is a double encapsulated frame, and again, this is one of the ethereal captures that isn't in your red book, and the folks in the back of the room are straining to see. Apologize. So you can see the tag there for the outer tag. You can see this is set to VLAN 1, and then the inner tag to VLAN 2. That's all you do to build this. You can pretty easily do this with libnet if you just build a .1Q tagged frame and then you use the .1Q implementation in OpenBSD or something as well. That'll basically create a double tag packet. And that's what we did in this capture that you see here. All right, so to deal with all these trunking related attacks, the first thing we recommend is just turn off auto trunking. This is very, very easy to do. The first thing you do when you turn on a switch is you should set all the ports off. turn the trunking off, and then you turn it on the ports that need to trunk. This definitely varies by not just whether you're running CatOS or iOS, but the platform itself. So right out of the Cisco docs, it says, the default mode is dependent on the platform. It's like, okay, thank you. All right, so best practices that we've talked about so far. These are the things to prevent the attacks we just talked about. So use dedicated VLAN ID for all your trunk ports. Disable any unused ports. I always like to put them in an unused VLAN as well, just because I'm maybe a little extra paranoid. Don't use VLAN 1 for anything, and then set your user ports to non-trunking. All right, so that was it with MAC flooding. We're going to talk more about MAC flooding a little bit later when we link it to a spanning tree attack. So ARP attacks, quick ARP refresher, very quick, 10 seconds or less. You basically are trying to figure out how to map the IP address to the MAC address for a given host. So I'll send out a network thing saying, how do I get to the guy in the blue shirt in the 4th row, and the guy in the blue shirt in the 4th row will respond back and say, here is my MAC address, and then we'll be able to talk. Basically all you're doing with ARP. Gratuitous ARP is the idea that I want to send out and let everybody know what my IP address is because it may have changed. A lot of high availability mechanisms will use this. That little nasty message we always used to get with like Windows NT4 when it would boot up and say, I've detected a conflict with the following MAC address and I've disabled your interface. That's a direct result of gratuitous ARP. Most operating systems do this. When they boot up, they'll say, is anybody out there my IP address? And if they get a response, then they'll basically honor that and allow the, in most cases they'll allow that MAC address or that interface to go down. So what if we went through and said, hey everybody, I'm the default gateway, and here's my MAC address, right? So we're going to talk through real briefly here DSNF basically and how it operates at some level of detail. So if you're already familiar with DSNF, I apologize. We'll get on to some different stuff in a few slides. So we're basically saying, all right, let's assume we've got this 1.2.3 network. We've got host X, Y, and W. We have the default gateway, which is .1. So there's no ownership, which is the big trouble with ARP, of either MAC address or IP address. Right? ARP was built during the days where everybody was happy and friendly on the internet, and no one would dare want to do something like what we're about to talk about. So if I was to just be host W and say, hey, I am in fact 1.2.3.1, and everybody should send packets to me, and I just wait a couple seconds and then I do it again. Well, what generally happens is X and Y will ignore it. Right? If they haven't tried to talk to the default gateway, they'll just let it go by on the wire. When host Y actually tries to talk to the default gateway, he'll talk out, and then the response from the ARP will be by the real default gateway, and the communications will be valid for a couple of seconds at least until that next timer kicks off and host W sends out that message saying he's in fact 1.2.3.1. At that point, host Y will happily update its ARP table with the new MAC address for that IP address. And I found that even if you're trying to use static ARP, particularly with NT4 and Windows 2000 for sure, it will allow it to be overwritten by gratuitous ARP. So you set static saying no matter what, this is always the MAC address for this IP. They'll respond back and overwrite it. So that's one of the opportunities to migrate. So Service Pack 2 for Windows 2K fixes it. Okay. All right. So DSNF. Yeah, I know Doug Song's website's down. He's got the petition against the DMCA. So I figured I'd give you some retro from his website. This is his feat. I got approval from him to use his feat in presentation. So long contract, actually, by the way, to get that signed off. So what DSNF is basically a collection of tools that will go through and do a lot of this stuff for you. And what this also did such a good job of showing you, and this is why I'm continuing to talk about DSNF, even though it's been around for a couple of years, is it shows how you can build additional attacks on top of that layer 2 compromise. So let's talk about it in action. We wrote a real quick batch file that basically says, I'm going to delete the default gateway's ARP address, I'm going to ping the default gateway once, then I'm going to show the ARP table. So you can see here's the ARP entry for the actual default gateway. Then I run ARP spoof, another very, very difficult to use tool. You type ARP spoof and then the address you want to spoof. And at that point, when I do an ARP A again, you'll see that the MAC address has changed. This is the core function of any kind of an ARP spoofing attack. Right? You can make this much more selective. This is a really noisy broadcast. If I was really trying to cause some harm, I would probably just ARP spoof my target to try and make the network a little less noisy. Okay, so now all the traffic is basically flowing through the ARP spoof box in a half duplex manner. Right? It's not quite a sniffer, but it's good enough because I'm seeing all the good stuff anyway. Port security helps not at all. right? Because I haven't spoofed a MAC address, I've just spoofed the ownership of an IP address associated with the MAC address. So the port security stuff, setting the limits on the number of MACs that I talked about earlier won't help. The attack could also be generated in the opposite direction. This is sort of a service attack a lot of service providers are concerned about. If this half of the room is McDonald's and this half is Burger King, and a packet comes in over a Metro Ethernet or something and says, who's McDonald's? If Burger King can respond before McDonald's, the router will happily start talking over to the side. So that's another way the attack can be run, and as I said, it can be a lot more selective. So once you do that, this is again building on that layer 2 compromise, because now that attacker machine will see all the packets from all the different hosts, and it will then forward as it wants to the real default gateway, and nobody will understand that their connectivity has been affected. So what I can run is this dsniff, and in this case I'm using -C, which is the half duplex TCP stream reassembly, which will allow me to look at all the 30 protocols you can see at the bottom of the slide and extract just the username and password. A lot of sniffers that are out there actually have to walk through and look at all the packets to see the result of the telnet, because most of us don't type all that fast. And this will actually just look for username and then grab what's right after it, look for password and grab what's right after it, and write it out to a file. So you could set this up and run, and I would be completely surprised if this hasn't been run at least once already here at DEF CON, and will probably be run all the time, or at Black Hat here, and then will be run all the time at DEF CON. So encryption. So there's other things that we can do once we have everybody's traffic, right? This is good. I went to the great Hogwash presentation. They were talking about modifying packets as they go through to do good things. Well, the hacker can also modify packets to do bad things once all the traffic's flowing through. One of the things he can do is make sure that any DNS request is always responded with the IP address of the attacker, right? So you try and go to Amazon.com, it tells you, 10.1.1.25. And the user, unless he's going to a DOS prompt and trying to ping to figure out what the IP address is, he's never going to know. He's just going to say, Amazon's kind of snappy today. And he'll send all his traffic on the wire. And once I've done this, I now can proxy every web request, right? This allows me to grab passwords, do anything, any kind of a man-in-the-middle attack against web. I can also do this with SSH. When you actually install dsniff, you build a real RSA cert, you put all the values in, you can present these credentials using OpenSSL to the user so that he sees these credentials come in. Raise your hand if you have never clicked yes on this message ever in your entire life. And we're the experts, right? We're the experts. Imagine what your aunts and uncles and parents are doing when they see this message. The security certificate was issued by a company you have not chosen to trust. What does that have to do with buying the latest Celine Dion CD? Absolutely nothing as far as this user is concerned. He's going to click yes every single time. And then you're going to have basically the credit card numbers. So upon inspection, if you click the view details, it will look invalid. But even a savvy user that's actually going to look, it's still going to look reasonable. You can see there the issuer was Amazon.com itself, which is a little bit suspicious. So anybody who's got a clue will actually see that this is invalid. So like many attack tools, many people create variations on this to make it easier, add functionality. AtterCap came out recently, and it doesn't support as many protocols to grab passwords as dsniff does, but it will ARP spoof both sides of a communication, which is really cool because now it allows real-time insertion into persistent TCP sessions. So I can have a live telnet session and make it look like you typed something you didn't, change what you typed, kill the session, hijack the session. So it's very nice, and again, very, very difficult for the script kiddie to use. So it actually includes online help, which I thought was kind of funny. All right, so here's an example of a mitigation technique that I'm not a huge fan of. How many people here are familiar with private VLANs? I don't mean regular VLANs, private VLANs. Okay, just a few of you. This is a great tool for some aspects of security, but doing it to stop ARP spoofing is, we're wedging it in at best. What private VLANs basically says is let's imagine everybody in this room is in a single VLAN, right? We'll have lots of broadcast storms. And what we do is we could say, I'm going to segment out different groups based on their function, but still have them in the same logical network. So we're all in the 1.1.1 network. I could basically go through and say, this section is in community A. This section is in community B. And you'll see each other's traffic within your local community, but you won't be able to see anybody else's traffic. I could also do this with isolated ports. I could say this whole section Each seat is its own isolated port. So when you sit on the wire and go to try and ARP anything, you're going to get no response except for promiscuous ports. So you can see here we've got some community ports set up, we've got isolated ports set up, and then promiscuous ports. This feature was originally built for a web hosting company that wanted a way to not have to burn a subnet for every single customer that they added. So we coded this feature. So if a community tries to talk to another community, the traffic's blocked. If a community tries to talk to an isolated, that's blocked. And if isolateds try and talk to one another, that's blocked as well. The real cool place to do this is in a DMZ. Right? If I've got a DMZ deployment, why not set up private VLANs so that my FTP server and my web server can't talk to one another if they don't need to, right? One of the first things an attacker will do once he compromises the first box is locally try and go get all the other boxes because he doesn't have to go back through the firewall. Well, what private VLANs will do is prevent that. Now, the trick is, and why this isn't so great for ARP spoofing, is typically people are ARP spoofing on user segments. So if you do private VLANs, nobody can talk to one another. So it sort of defeats the purpose of a network in the first place, which is you want to try and share information. So this, in order to use this in a way that would prevent ARP spoofing and still have the network function, most of your resources would have to be someplace else. Most of the time, the users are talking to servers as opposed to one another. And again, 100 pages or so at the link at the bottom. All the private VLANs are not the same. We've got them in most of the platforms. On the higher end switches, they're called private VLANs. The mid-range and lower end stuff, they're called private VLAN Edge. They vary a little bit. The higher end switches have something called sticky ARP, which sort of mitigates the reverse attack that we talked about. Once someone sends a packet, it binds the ARP entry and the MAC address to that port permanently. If you ever need to change it, you have to manually go in and clear it out. So it's, it's very secure, but it's also not the most friendly thing to try and troubleshoot. And it also will allow you on the higher end switches to span multiple switches with private VLANs and to do the community ports. But in general, most people just need the isolated ports and the promiscuous ports. And in that case, it's fairly easy. Private VLAN configuration in CatOS is kind of a pain. I've got a whole slide, next slide, that walks through how to do it. On iOS, it's really easy. You just say port protected, and then that means the port's isolated. If you don't type that, it's a promiscuous port. So with CatOS, what you first have to do is go through, if we walk through, first you set up a VLAN and say, this is a private VLAN primary. This is my primary VLAN. Then you can do a show pVLAN, see that VLAN 41 is part of it. Then you have to create your isolated VLAN. So you'd say, set VLAN 42 isolated, pVLAN isolated. Then you have to map the two of them together. So you say set pVLAN 41, 42, and then you have to set the ports that should be bound to that mapping. And that will basically create isolated ports for ports 39 and 310 in that. And then the VLAN isn't really referred to as VLAN 41 or 42. It's referred to as the group 4142. Then you just have to map the promiscuous port. So if you've got a router port or an MSFC off of the switch, you just have to bind that through this set pVLAN mapping command, which is pretty straightforward. All right, other things you can do for ARP spoofing. Many IDS systems will watch for large amounts of ARP traffic, right? If it sees lots of messages, it'll flag an alarm, which is nice. ARP Watch is a freely available tool which will watch ARP bindings, so you can watch for changes in the ARP tables for things you really care about. You could use static ARP for really critical servers, default gateways, critical devices, but again, administratively, you have to wonder if you're really going to be able to manage this over time. And then Cisco's working on sort of an ARP firewall, which is going to be deployed here in some of our higher end switches to allow you to control ARP entries from all the different devices. All right, spanning tree attacks. How many people here are a spanning tree expert? 1, 2, all right? How many people here forgot, not even enough, they want to forget more about spanning tree? Yeah, I count myself in that group as well. It's like you remember at some point in your networking career you learned about spanning tree and then you quickly forgot about it because you said, ooh, an IP address, that makes sense. So what spanning tree is trying to do is maintain a loop-free topology. That's basically all you need to remember to talk about the attacks. If you have multiple switches with multiple paths and you don't have spanning tree, broadcasts will become storms, and really quickly, I was doing some testing, and Ethereum went from 1 packet to 300,000 packets in 3 seconds when I did a ping. So it's really, really nasty. And how many people here have dealt with some kind of a broadcast storm on their own network? Okay, probably 10% of the room. So what happens is a tree is elected root. Everybody sends out these BPDU messages, Bridge Protocol Data Units. And what they have inside them is a priority. So they set that priority. The default on most devices is 32,768. and they send that priority out, and whoever's got the lowest number, if they all got the same, it defaults to the lowest MAC address. That switch becomes the root, and then the spanning tree topology is built based on that root bridge. So you can see here, whoops, the root switch is up here in the upper right, and it's set to forward, and then this link is set to block because it's trying to avoid the loop. So in this way, you won't have any loops going on the wire. The other thing to note is spanning tree is very, very simple. There's really no notion of a payload. It's just a standard 802.3 packet. It's got very few options. It's basically just sets flags. I've got a capture of it on the next slide. So they have things like a configuration message, which will basically just say, here's the root bridge and its priority. They don't actually exchange topology information. All the topology is derived based on where the messages come in and what priority they're set to. You can also have something called the topology change notification and then a topology change acknowledgement. And that's going to matter on the next slide when we talk about some of the ways that you could attack networks with poorly deployed spanning tree. So different attacks. So the easiest attack is just basically changing the topology somehow. If I can change the topology by sending out a BPDU or something like that, basically it takes about 30 to 45 seconds. And the testing that I did, if I didn't tweak any of the values on the box, if I introduce a link that would be looped and needed to be blocked, or if I failed a link that was primary and needed to fail over the backup, 30 to 45 seconds, right? So I keep doing that, and that would be a nice DOS in and of itself. Very annoying one, admittedly. There's some features. Cisco's got some features, and some of the other vendors have some features like port fast and uplink fast, which will allow you to converge that time down significantly. So what you can also do is a topology change notification is spanning tree saying there's been a topology change and everybody needs to relearn where everybody's located, right? So what we do with the TCN message is we age out that CAN table we were talking about with MAC flooding. The default, if you remember, was 300 seconds. A TCN message will take it from 300 seconds to 15 seconds. So if I was trying to go after and MAC flood as many systems as possible, I would coordinate that with the TCN message, which would age everybody from 300 seconds to 15 seconds. And although lots of folks talk every 300 seconds, not so many people talk every 15 seconds. So if I was to send that TCN at the same time that I'm MAC flooding, I'll probably knock most of the people off the network unless they're really chatty or in the middle of a download. We also found, we originally were thinking, should we build some of this stuff out with libnet or whatever? In actuality, you don't need to do any of that. I was just using an OpenBSD box, and you just turn on, you use brconfig, just like ifconfig, and you say brconfig, bridge 0, and the interfaces you want to be in the bridge, and then whether or not you want it to talk spanning tree, and if you want it to talk spanning tree, what priority you want it to set to, and then all of a sudden it's a bridge. All the layer 3 stuff keeps working, at the same time it's a bridge. So this can yield to some more interesting attacks. You can see here on the right, this is just a screenshot for your benefit of a regular configure message. So you can see it's really simple. When you actually get down to spanning tree, it's just got some flags, whether it's a TCN or a TCA. It identifies who's the root and what MAC address they're located at. So let's talk through an attack example. So if I'm the attacker and I have dual homed myself to 2 different switches, right? I was originally thinking, well, this is just going to be a theoretical attack, but then I thought lots of folks have switching set up where they have stackable switches, right? They have lots of switches at the access layer. Well, if I plugged into a port in one cube and then took a long cable and plugged into a port in another cube, very likely I might be on another switch. So if I'm able to do that, then I become a bridge myself. So I send this out to try and become the root bridge. You can see what will happen is the root will change. You saw it move there down to the attacker. Spanning tree will then recalculate. His local links will go into forwarding, and the link between the access switches will go into blocking, which is a DOS attack in and of itself, right? And then the traffic will basically flow through the attacker, right? So we verified this very easily in the lab using brconfig. And everything we could do with dsniff, now you can do with spanning tree, right? Everything flows through, and actually I was lazy in the lab. I didn't want to deal with configuring the bridge on 2 interfaces on my BSD box, so I just plugged in a hub and plugged the bridge port into that, and then plugged the 2 uplinks over to the two other access switches. And that was a really great denial of service attack too, because I had gigabit links between my 2 access switches, and I had a half duplex 10 megabit hub connected to my attacking BSD box. And although spanning tree is topology aware, it's always from the perspective of the root. So if you are root, you get to decide the topology effectively through the way that the spanning tree protocol works. So I took a gig link to a half duplex 10 meg link. Right? So that's pretty nasty, in addition to the fact that I'm now seeing all the traffic flow through the attacker machine, and I can do whatever I want to the traffic. Okay, so if we try and do some applied knowledge and take all the attacks that we talked about and try and do something interesting, this is again not in your books. Let's walk through one of the goals. So let's assume, I'm sitting off of an access switch and I want to get access to traffic going between a couple of chatty servers that somebody's basically done static ARP, right? So I configured static ARP, and so they're really chatty, and so I can try and do some things, right? What if I cam flood, right? Well, I cam flood, they're so chatty they never age out. They're even chatting faster than every 15 seconds, so they're never going to age out. They have static ARP, so ARP spoofing isn't going to work, right? So what I start by doing is MAC flooding the access switch. The traffic between the two servers, let's assume, is flowing through these two distribution layer switches here. So I flood the access switch because the access switch doesn't have that server communication at all. After I do that, then I run brconfig, set up the bridge on my attacking machine, set myself to priority 0. I become the root. The topology gets reconverged based on that. You'll see the root move from the access switch down to the attacker machine. Spanning tree is going to recalculate. So the access switch now is set to forwarding. So now I've got, again, a nice denial of service. If I had a giggy backbone link and fast uplinks, or maybe I had 10 gig on my backbone and giggy uplinks, now I've already created a nice denial of service. But now what winds up happening is I filled the CAN table on the access switch already. So now when spanning tree reconverges, that chatty server tries to talk through the access switch, and the CAN table's already filled. So then he has to flood. Right, so this is a way that you can get a chatty server on one switch. If you can get him to go through another switch and you flood the switch before, you can then start seeing all the traffic just like you would if you were flooding him locally. So I tested this in the lab and it worked fine. So the good news here, I get to be a bit of an optimist now, spanning tree attacks are very, very easy to stop. Right? So there's two features. One is called BPDU guard, and this is a feature I found out about the hard way because we have it implemented at Cisco, is basically what it says is you plug in a switch or anything that talks spanning tree into the network that's configured with this BPDU guard turned on, and it turns the port off. Right? So I was trying to plug a switch in to do some of my lab testing. I had a bunch of boxes, and I plugged in the switch, and my link went dead. Damn, what's going on? So I went and talked to everybody, and we found out about this feature, and then it was implemented. So it's very easy to fix, right? I just turned off spanning tree on my switch, and then everything worked just fine. Question? Yeah, I changed my mind. Or my mind was changed through the collective learning of everyone. So what we were talking about originally, some people have recommended this, and I wound up taking their recommendation without thinking it through myself, that the best way to deal with spanning tree is to just turn it off, right? Because that eliminates everybody from being able to reconverge the topology. If you don't have loops, why run spanning tree? Well, then if you don't run spanning tree, then another nice attack from the attacker's perspective is to introduce a loop. And now I've created a nice denial of service attack. So the way to stop these attacks is so easy using spanning tree. I'd rather have just people leave spanning tree on and configure these features. So you basically, any port fast port, which in Cisco terminology is just a port you've configured as a user port, will basically globally be put in this BPDU guard. There's a slightly less hostile feature you can turn on called root guard, which is available on some different switches. And what root guard does is say, you can talk BPDU all you want, you can talk spanning tree, as long as you don't decide to become the root bridge. If you do that, then I shut you off. There's a question over here. Yeah, so the updated slide deck, we'll get it to the Black Hat website as soon as possible. All right, so that's how you stop spanning tree attacks. All right, so now let's shift gears and talk about VLAN trunking protocol. Is anybody here using VTP on their own networks? Maybe just a few. Anybody like it on their own networks? It was built originally to be a convenience feature. We wanted to share VLAN information between lots of different switches. So we wanted to say, all right, I configured 25 VLANs on this switch. I want to propagate that to all the other switches so I don't have to manually configure it on all these other switches. Unfortunately, most people, and I count myself among this group, get a little uneasy when you start doing configurations for the administrator. I want to know exactly where my VLANs are. So for those people, just don't use VTP. But folks who are using VTP, please use the MD5 digest that's available with VTP, which will just add, it'll add the digest to the message so you can at least be assured that the communication is reasonably authenticated. Again, this is another one of those 802.3 with Snap. The Snap protocol type is 2003, so this will all show up in Ethereal. So potential attacks. So one of the attacks you could do is if you are able to become be able to speak basically VTP, you could become, there's this notion of VTP server and VTP client. If I become a VTP server and I have the domain name, which is all sent in the clear, I could basically create a new configuration revision which has all the VLANs deleted. And then all the other switches will happily say, well, the server told me that there should be no VLANs, and it will delete all the VLANs. Right? So this is an attack that I found out about actually had happened to someone through misconfiguration, and it was one of the reasons they're not running VTP anymore. This is one way to do it. You can see the capture here, and it's pretty straightforward. This is actually the first of two messages. The second message contains all the VLAN information. Question? Right, so the question was, Cisco switches, when you first turn them on, are configured to be VTP servers. You still have to set the VTP domain, though. So you have to manually, as a user, set the domain, which would then cause all the VLANs to be overwritten. So you have an opportunity there to switch it to client before you set the domain name. So very easy to turn off. Just say set VTP mode transparent or off. Depending on the switch, you'll have different options. You can basically turn VTP off. All right, so there's some other things we can do. At layer 2, there's this layer 2 port authentication. Is anyone here brave enough to actually run VMPS, VLAN Management Policy Server? This is the mechanism to take a MAC address and associate that MAC address with a given VLAN. So I can set it up so everybody here can be divided based on their functional group within an organization, and based on you connecting, it will learn what MAC address you are, look you up in a table, and then assign your VLAN. Right? Again, for the same reasons I recommended not to do port security with a lot of different MAC addresses, I recommend not to do VMPS, because managing all this VMPS stuff is very, very painful. Again, MAC addresses are NICs fail. It's going to be very painful to maintain the database. So it uses a protocol, there's another reason not to do this, called VQP, VLAN Query Protocol. This protocol is UDP-based and is completely unauthenticated. So if you're using it for a security reason, you should be worried, because it's all being sent in the clear anyway. Basically, if you fail that violation, or you're a MAC address that you don't know about, you can set the default policy to give you a default VLAN that maybe has limited functionality, or to just not let you on the network at all. So the way it works is you have this VMPS server, which is typically a switch. Then you have a VMPS client. So the database gets pushed to the server over TFTP. It's a flat file database that basically has all the MAC entries and what VLANs they should be on. The client connects, and these VQP messages are sent between the client and the server. And again, it's all sent in the clear, UDP-based, very easy to spoof. There's no tools I know about this today, and that's mostly because people would have a hard time developing a tool that 1/10 of 1% of Cisco switch owners might actually run. You can see Ethereal doesn't even decode it, which tells you how often it's used. Ethereal decodes just about everything, right? So that they don't decode this is indicative of how often it's used. But you can see it's basically just running on a couple of UDP source ports. This is the VQP query here. You can see in the message FA08, which is the message of the port that is trying to authenticate, and that it's currently set up to the none VLAN. You can see right after that, the none VLAN over here. So, you could do some different things if you were able to spoof this. You could basically get on VLANs you're not supposed to, prevent other people from getting on VLANs, delete the configurations out. The response you can see come back, and here you can see it's assigning the user to VLAN 8. So if you have to use VQP or VMPS, do it out of band, meaning send your control traffic, your SC0 interface on your Catalyst switch, set that to a different VLAN, different IP range, so that it doesn't get sent over the same links that your user traffic is sent on. And if you've got the bodies to deal with all the MAC address tables and entries that are going to change on a daily basis in a large organization, you probably have the resources to deal with this security. Like I said, most people aren't using this. So 802.1x EAP, I'm not going to spend a lot of time on this because there was a whole 802.1x talk at Black Hat. But the basic idea is this is a standards-based way to do what I just talked about with VMPS. I can basically do EAP over LAN across 802.1x and send messages back and forth to authenticate a given user to a given domain. There's an open source implementation of it. It's natively supported in all flavors of Windows XP. And Microsoft has made some rumblings about back converting it, though I haven't seen any commitments yet. So real quick, what it looks like, the client basically has his ID requested by the switch. The switch responds with his ID, or the host responds with his ID and password. That gets forwarded on via radius. So keep in mind the 802.1x is really only between the user and the switch. The switch sort of acts as a middleman. He forwards that inside radius or whatever other mechanism you've chosen to use for your EAP transport. That comes back from the ACS server or the radius server and gets sent on to the switch who's accepted. So this is another way to do this. This is interesting, new technology. I'm not sure that I'd recommend everybody run it on their production networks today. Over time, I think some of the things we can do with 802.1x will be interesting. If we can do things like enforcing antivirus signature levels or personal firewall policy levels and do that kind of thing through 802.1x, that could be an interesting way to try and make the average user a little bit more secure. Also to note, the University of Maryland paper that came out attacking 802.1x was primarily attacking 802.1x as implemented for wireless, which if you were at the 802.1x presentation earlier, 802.1x never really developed for wireless. Question way in the back.
I'm wondering if an attacker can send a host a request ID packet and get the host to send back ID and password with the expectation of being authenticated on the network.
So the question is, could the attacker send this message directly to a user as he connects to the switch? I'm not sure that the messages would actually be propagated through the switch because I think they're all going to be just local messages without, because they're not going to have any IP addresses. So that'd be an interesting thing to talk about afterwards. It's all going to be at layer 2.
Is it flood to unauthenticated ports?
Is it flooded to, is the mess? Okay. No, because the message is at layer 2. The question is, would it get flooded to the port? The messages are all exchanged locally. There's no IP addresses associated with them. No, you shouldn't. You shouldn't. It's set up with EAPOL. It always has an open EAPOL, EAP over LAN hole, basically, so you can send the initial authentication request, but everything else should be dead. So there's some other attacks, not that they're any less significant, just that they didn't really have a nice category to go into. So CDP. CDP is the Cisco Discovery Protocol. It's a proprietary protocol, again, using the same 802.3 packet, the Snap Protocol types 2000. It is a great information gathering protocol for a network administrator or for an attacker because it's going to give you a lot of information about what version of code the Cisco devices are running. And also, this is something that you don't see when you actually look at it on a Cisco device. I captured this off Ethereal. It has this capabilities setting where it'll basically say, will this device do layer 3 routing? Will it do bridging? Will it forward ICMP messages? Will it provide all this different functionality? So all these messages are sent in the clear. So Ethereal will decode this stuff happily and let you know what VLAN you are on. You can see down here the native VLAN. So that's going to be useful if you're trying to do VLAN hopping. You're going to have to first determine what VLAN you're on. Well, CDP will tell you that. So the easy thing to do is just to turn CDP off if you don't need it. Keep in mind that Cisco developed CDP for a reason. Some applications make use of it. So one of the things to think about is maybe allow it to run on uplink ports but not on user ports. You're going to have to decide based on your own policy what settings you want. All right, besides this information gathering benefit that CDP would provide an attacker, there was also an attack that FX at Phenolit found that basically we didn't do any bounds checking for our CDP database. So if you just sent a bunch of bogus CDP router, hey, I'm another router connected to this port, you did that over and over again, eventually it would run out of memory on the router or the switch and the switch would crash. Right? So we fixed that, but the reason I bring it up is because these are the version numbers you have to be running to not be vulnerable. As you can see, there's no 11. Release, there's no 12.0 release. So you've got to be running fairly new code to not be vulnerable to this attack. So I bring it up because it didn't get a whole lot of press when it first came out. You can see the CERT advisory and the Cisco advisory there at the bottom. I'm not the question is there a device that I can't get the newer version of code to not be vulnerable to this attack? We'd have to take a look at the advisory to find out for sure. I mean, I don't know like a 1900 series catalyst switch. I'd be real surprised if you could get really, really new code for that. But that'd be something we can check into. All right, so DHCP starvation. This is another attack that if at layer 2, I can basically do the same kind of thing I did with MAC flooding, except this time grab all the addresses running over DHCP, right? So if I could say, all right, there's 300 addresses available, and I'm going to grab all 300 addresses. Now I've got a nice denial of service, first of all, because the other users that try and connect will basically not be able to get on the network. I could also, even if I didn't do this starvation attack, I could introduce a rogue DHCP server which would hand those messages or hand the DHCP messages to the user. So the user would get a DHCP offer message from a rogue server. And if I got that DHCP offer and that user accepted it, I would probably have set as the attacker the default gateway, the DNS server, the WIN server, the IP address, all those cool things I get to set with DHCP. I would set it to my attacker's machine. So then now all the traffic is going to flow through me much the same way it would with an ARP spoofing attack. So this is another thing that you can do with DHCP. So the trick is the same techniques that you're going to use to mitigate CAM flooding, the port security, the idea of setting the maximum number of MAC addresses that can live on a given port, that will stop the denial of service attack against DHCP. But unfortunately, it won't stop the rogue DHCP server. And that's because of the way the RFC is for DHCP. You can see some cut and paste from that RFC. I won't read it for you, but the gist of what it says is the client collects any and all DHCP offer messages received from any amount of DHCP servers. And the method by which that DHCP client decides which address to check is implementation dependent. So any OS can decide whatever mechanism they want. Some obvious mechanisms they might use would be to accept the first one, maybe, or to accept the one from the server that they previously communicated with. I haven't done all the testing on all the different operating systems to figure out what method each one does. If somebody wants to do that, that'd be a great thing to know. But basically, in order to fix this, we really got to deal with improvements to DHCP in general. So we coded, Ralph Droms at Cisco wrote this RFC 3118, authentication for DHCP messages. And it, unfortunately, is sort of a victim of the chicken and egg problem in that he's written this way to authenticate DHCP messages, but the clients don't support it because the servers don't support it, and the servers aren't supporting it because the clients don't. But it basically specifies two ways to do DHCP authentication. One way is a simple clear text token. The other way is to do a more sophisticated HMAC, MD5 kind of an exchange to authenticate the messages. But that's going to require distribution of the keys out of band, so from a manageability standpoint, it could be very, very difficult. Cisco's also developing another, sort of like our ARP firewall, we're trying to do something with DHCP as well to limit who's allowed to respond to DHCP requests, who's allowed to see DHCP requests. We already have some of this functionality in 3550, which with this DHCP option 82 feature, which was coded for service providers to allow you to associate the MAC address binding with a port as opposed to with a MAC address. You can basically use this feature so that other user ports will never see DHCP requests, so that the attacker will never see, the rogue DHCP server will never see that request, so it'll never be able to respond to it. So the reason this attack wasn't coded sooner is because DHCP, unlike CAN table flooding, requires a few packets. So if you're trying to attack and grab all the addresses, you have to do a couple of messages with DHCP to actually get an address assigned to you. But I was just on PacketStorm the other day, and somebody had coded the attack, and I haven't played with the code yet. If anybody else has, I'd love to talk to you afterwards to figure out if it works. But he's saying this will basically grab all the DHCP addresses that are available. So other best practices would be doing things like not using the same DHCP server for every single security zone in your network. You're saying you can renew an address that somebody else had owned previously? Yeah, so DHCP has absolutely nothing from a security standpoint by default. So any of the messages that you can send, any place you can spoof a MAC, any place you can spoof an IP address, you can basically do anything you want with DHCP, much the same way. You could, yeah, it does have sequence numbers. So, all right. So I just talked about private VLANs from a security standpoint in preventing ARP spoofing. Does anybody here know that they're also vulnerable? So now I'm going to talk to you about some of the security issues with private VLANs and what to do about it. So let's assume I've got an attacker and a victim, and they're connected to isolated ports. Remember, private VLANs, I'm segmenting one VLAN to be basically further subdivided into functional zones. So I have the attacker and the victim. They're both isolated ports. Let's assume the attacker's a web server and the victim's the FTP server, and I've compromised that first web server. Now I'm trying to get at the FTP server. Well, if I just try and go directly and I send it from source A1, MAC A, IP1, which is the attacker, and send it to destination B2, which is the victim, the private VLANs are going to work just fine and drop the traffic. The trick is, if the attacker sets his source to himself and the destination MAC address to the router and the destination IP address to the victim, what's going to happen? Well, private VLANs are going to work because from a layer 2 standpoint, you're not trying to talk to another isolated port, you're trying to talk to the router. So the router, the switch is going to forward that traffic to the router, and routers being the nice guys that they are, because they have to comply with all these RFCs that basically say, under any circumstance, if you can figure out a way to get the packet to where it's supposed to go, get it there, the router's going to forward the packet. So he's going to say, oh, you're trying to talk to MAC address B. Well, let me recode it for you, put the right MAC address on, send it back out on the wire, and then the victim will receive the packet. So the thing to know is that although this isn't a private VLAN vulnerability, because private VLANs did what they were supposed to do, what you wanted to do with private VLANs didn't happen. So it's only unidirectional traffic, unless I've compromised both hosts through some other means. Then I can very easily just set a couple of static ARP entries and get the traffic to flow through very easily. The other thing to note is firewalls will not behave like this because they're not under the same strict RFC compliance that routers are, and that a firewall is going to see, hey, you're trying to talk to a guy who's on your local segment, you shouldn't be talking to me, and it will just drop the packet. So when we're trying to mitigate this attack, we don't actually make a change to private VLANs. What you have to do is set up an ACL on your ingress router, basically saying any traffic from the local subnet to the local subnet, drop it on the floor. Fairly easy to do. You could do this with a VLAN ACL as well, but it's sort of a layer 3 problem, so I'd recommend you do it with a router ACL. All right, there were a couple of other things that we had the at-stake guys do that wound up not yielding any results in terms of doing any kind of VLAN hopping. We had them just, they spewed a whole bunch of multicast traffic, multicast MAC addresses over and over and over again over a weekend, and then tried to insert traffic that would hop, and that didn't work. They also did the same thing with just completely random Ethernet frames. So they would just send garbage, for a weekend and then try and insert traffic to get to another VLAN, and that didn't work either. All right, so IP telephony. How many people here are using IP telephony? Okay, so a fair number of you. So one of the best practices in IP telephony, at least Cisco's implementation, is to use multiple VLANs. You have a voice VLAN and a data VLAN. Right? And this is one of many things you need to do in order to try and make IP telephony as secure as you can. So the way that message gets sent to the phone, so the phone knows what VLANs to use, is via CDP. So I talked about CDP being used in some places. This is one of the places that it's used. So we set up this auxiliary VLAN, which is what the traffic is tagged from the phones to basically flow over the voice VLAN. So you can see this is just TCP dump output. All the traffic is set, and you can see it tagged. The auxiliary VLAN is 987. So it's tagged as a .1Q packet and then sent in the clear as well. This message is sent so that the phone will then learn what VLAN it should use, and then it will tag its own traffic with that VLAN and PC traffic, because if you're not familiar with IP telephony, typically you'll have multiple ports. You'll have the port that goes to the switch, then you'll have another port that connects to the PC, so you don't have to do 2 uplinks for every user. What Cisco's implementation does, and this is a feature by the way, is we broadcast all of the traffic coming in from the uplink port destined for the phone, we send that to the PC as well. Right? Because if you're trying to troubleshoot a problem with your phones, it's going to be very difficult to do with the phone itself because it has very limited troubleshooting. So we forward all the traffic to the user, basically, and then he can see the traffic and do whatever he wants with it. We also had originally a vulnerability where you could pretend to be the phone by your PC and just be connected directly to the PC port on the phone and spoof the MAC address of the phone. That still works just fine. You can spoof the MAC address of the phone, but previously we wouldn't even send a reset to an unacknowledged TCP session that came back to the phone. So if you would send a TCP request from the PC to some device on the voice network, the ACK would come back to the phone. The phone, on seeing an unrequested TCP ACK, should send a reset, right? Well, he wasn't, but he was still forwarding the traffic onto the PC. So if you remember a month or so ago, we had a CERT announcement, a vulnerability with IP telephony in general. So we cleaned up a lot of that code, and it's a bit more secure right now. So the other reason I bring this up is those of you who are using IP telephony, you're going to have some of these features that I talked about during this presentation are going to work, and some of them are not going to work. So when you're trying to figure out what you want to do, basically private VLANs don't work at all, and 802.1x doesn't work at all when you're using phones. And the reason we care about phone security is because today phones have no confidentiality. So there's this tool called Vomit, which folks have probably heard about. It stands for Voice over Misconfigured Internet Telephones. And let me try and shoehorn this acronym to work. I want it to be called Vomit. What words can I use? And what it does is it basically takes a voice stream and dumps it out to, via TCP dump, and dumps it out to a WAV file. So you can imagine the damage you could cause having access to a CEO's voicemail a week before earnings announcements, that kind of thing. So Vomit's kind of more of a proof of concept tool. It only deals with one codec, so it's not really this robust DSNF-like tool to do this. But because things aren't encrypted, that's one of the reasons why you really care when you're trying to deal with IP telephony. So the other thing to talk about is management. When you're dealing with management, we'll go through this real fast. All this stuff we just talked about doesn't mean anything if the attacker just telnets into your switch and turns everything off. So when you're dealing with a switch, just like when you're dealing with a firewall or an intrusion detection system, you need to start migrating to things like SSH, like SCP, trying to make things as secure as possible. If you can't use security protocols, you need to try and migrate to out-of-band management, for example. So running all of your management traffic off a separate VLAN, potentially physically backhauling that link someplace else on the network so that nobody else can see it. Question?
Yeah, SSH2, I know you guys have been promising it for probably 3 years. Any future dates?
Oh, now we get to the Cisco bashing. Cool. No, I know what you're saying. Yeah, so I haven't heard Cisco make any kind of a commitment that we're going to do SSH v2. I know that's been requested. I know SSH v2 just got finally standardized now within the last several months. So now that it's completely done and standard, I'm certainly not going to make any commitments because now I'm not in charge of any products myself. I'm just a security guy. So one of the things to note is the vulnerabilities that are in SSH 1.0. We use SSH 1.5. Cisco's implementation of SSH is not vulnerable to any of those vulnerabilities. So the impetus for folks when we explain that to them to go to SSH v2 tends to go away. That said, v2 is the current protocol. It's now standard, so I would be surprised if over time we don't do it. So I'd be happy to talk to you offline, and I can get you the names of some product managers, and I can forward your information over to the relevant folks. Today you've got SSH in a couple of the switches now. We're obviously going to be migrating it to more and more devices as we start caring as Cisco, because our customers are starting to care more about dealing with security at the campus. All right, so quick case study. Real quick, here's the best practices. I'm just going to go through these as kind of a summary. Many of you have probably read that Improving Security on Cisco Routers doc, or there's a new O'Reilly book on hardening Cisco routers. Fortunately, there's not that same due diligence on switches. So you can use this kind of as a cheat sheet for some of the functions that we recommend people do if they're trying to deploy a switch in a secure manner. Keep in mind, none of this means anything if your security policy dictates that you want to implicitly trust all of your users that they won't do anything wrong, right? If you have a policy that violates and says we shouldn't be doing port security, great. I'm much more happy that you have a security policy than that you turn all these bells and whistles on. So, does anybody have a part of their network that looks like this? Nobody? Okay, I should have said, who doesn't have a part of their network? What this is I see this all the time. I'm asked to justify it. I'm asked to confirm whether or not it can be done in a secure way. What I've tried to show is over the course of this talk, At Stake did not find any method. We did not find any method as Cisco to VLAN hop, right? If we configure things properly, all the things we just talked about over the last hour and a half, if we do all of this, we weren't able to get VLAN hopping to work. That said, am I going to stand up here in front of this crowd and say we will never have a VLAN hopping issue on a Cisco device ever again? No way in hell. You couldn't pay me enough. What I will say is if you use reasonably current code and you try and deploy all the best practices that we talked about, you can mitigate the risk. Many people do this for reasons other than security. One of the big ones is physical rack space, right? They don't want to have to deploy 50 switches for all the different links, so they deploy a couple of bigger switches and then deal with VLANs. So it's technically possible to make this secure, at least given the testing that we did. But what happens if that switch gets compromised, right? So this is the idea of using one VLAN or two VLANs on a switch to basically control two different security zones on the network, right? This is one of the big things that we've sort of been espousing that folks should really think hard about before they do. And nothing's really changed that about our testing. Even though we weren't able to find a way to do VLAN hopping, assuming they're configured properly, I still wouldn't stand up here and say this is a particularly good idea. Because if the switch gets compromised, you've got problems. Also, the security operations guys don't generally control the VLAN settings on the switch. So now you're relying on NetOps guys to make security decisions, which probably raises the hair on the back of the neck of many of the security guys in this room. Also, you need to remember, and this is the one core thing to remember, is that your security perimeter now includes the switch, right? If either the firewall or the switch is compromised, I can bypass the security controls that I've put in place on the firewall. So a more secure alternative is fairly straightforward. Use multiple switches. Then I can make sure a misconfiguration on the switch won't allow somebody to bypass the policy. And my security perimeter is now contained just to the firewall. So again, if configured properly, Cisco's and NetStake's testing during the platforms that we decided to test, the 2950, 3550, 4K, 6K, CatOS, and iOS, we did not find a way to VLAN hop, assuming you configured everything properly. We talked about some of the things that we did discover throughout this presentation if you've got them configured improperly. That said, I think I'm pretty much done. There's a lot of links down here in terms of all the things we talked about in the presentation. Before I was doing this critical infrastructure role, I did a lot of the safe blueprints. So if you've heard about the safe architecture from Cisco, I've written a lot of those white papers myself. Is anybody here going to change anything in the way they're doing their layer 2 network based on something they learned at this talk? All right, fair number. All right, thanks very much. I'll be up here for questions.